for truly autonomous surgical robots.
It's one of the highest stakes applications of AI imaginable. I mean, the promise of robotic surgery has always been immense.
Oh, absolutely. You think of enhanced precision, far beyond the human hand, tireless superhuman steadiness.
And reduced surgeon fatigue in those marathon procedures. But for years, that promise, that idea of fully autonomous capability, it's been held back by this silent, invisible constraint.
And that constraint is data scarcity. It's the Achilles heel of modern robotics.
Yeah.
But in surgery, it's a full-blown crisis.
It really is.
We've seen foundation models like RT2 and now GR0T. They've completely revolutionized general robotics, giving us these highly capable machines that can move based on simple commands.
But they thrive on mountains of data, specifically large-scale paired vision-language-action datasets, or VLA.
And that pairing is everything.
It's the critical factor. These models need, well, billions of data points where you have the visual observation, so the video feed perfectly synchronized with the language instruction, and most importantly, the exact mathematically precise robot control command, the kinematics.
For general robotics, that's, I don't want to say easy, but it's doable. Google and others can generate these data sets in simulation or in these huge warehouse environments, just collecting millions of paired actions a day.
But operating rooms are not warehouses.
Exactly.
And in surgery, that gold standard paired data is, well, it's nearly non-existent on the scale you'd need for these modern VLA models. We are talking about prohibitively expensive, limited access operating rooms, strict patient safety protocols, and just intense regulatory hurdles.
You just can't do it.
You simply cannot gather the diverse, scaled, synchronized data needed to teach an AI how to perform complex, nuanced actions like suturing or needle handling reliably across thousands of different anatomical scenarios.
You mentioned the cost, and that's a huge factor. A modern robotic surgical system can cost millions of dollars, right? And the time to operate it it's astronomical.
Yeah, you can't just rent 1 million hours of surgical robot time to collect data.
And even if you could, even if money was no object, there's the ethical wall.
That's the real blocker. The most valuable data in vivo trajectories, so movements inside a living patient, those are restricted by patient safety, privacy laws, and all sorts of regulatory limitations. So the data that does exist is sparse, it's non-standardized, and it's often missing the crucial kinematic action labels you need for policy learning.
So if the data is scarce and expensive and the simulation tools are inadequate, how do you train a data-hungry AI when data is scarce? I mean, that fundamentally is the mission of this entire deep dive.
The answer we're analyzing is the SurgWorld framework. And this is a really remarkable collaboration developed by NVIDIA and multiple research institutions specifically designed to just break this bottleneck wide open.
So how do they do it?
SurgWorld flips the script entirely. They decided to stop chasing scarce real paired data and instead synthesize it using the vast amount of unlabeled surgical videos that already exist.
So instead of capturing the action, they're inferring it.
They're inferring it. They are fusing those unlabeled videos with incredibly precise human expert text labels to train a world model. This model then generates high-quality synthetic video rollouts.
And here's the magic part.
And crucially, they use a second model to infer the precise robot control commands that would have been needed to generate those videos.
Okay, let's unpack this. How do you train a data-hungry AI when data is scarce? Our roadmap today covers 3 key pillars that make SurgWorld a game changer. First, we need to understand the human-in-the-loop effort, the creation of this highly specialized surgical action test alignment, or SATA Dataset. Second, we'll look at how the SurgWorld model itself generates these photorealistic and, importantly, generalizable surgical video rollouts.
And third, we'll dive into the absolutely critical technical bridge, using inverse dynamics models to infer those robot commands, which they call pseudo-kinematics, that actually train the downstream policy.
This represents a shift from data collection to data generation.
It's a critical step if surgical autonomy is ever going to become scalable.
Okay, let's start by reinforcing the root cause of the problem. We've established that general robotics can gather data easily, but the surgical environment imposes these unique constraints. Why exactly do traditional imitation learning methods fail so spectacularly in this specialized domain?
Well, traditional methods like behavior cloning, they require the robot to perfectly mimic an expert demonstration. If the demonstration is a video, you need the corresponding trajectory of the robot's movement.
The action part of VLA.
Exactly. And in surgery, the data collection fails on 2 fronts. access and fidelity.
Let's focus on cost and access first. We touched on the expense of the systems, but what about the logistical bottleneck?
Logistically, accessing an operating room, which is a controlled, sterile, high-risk environment, is incredibly difficult. You are constrained by scheduled surgeries, patient flow.
Right.
You can't just set up a camera and recording equipment for weeks on end and run thousands of trials. Data collection becomes an interruption to patient care. It's not an independent research endeavor. And this inherently constrains the scale and the diversity of the real data you can acquire.
And as we touched on, the ethics and safety component fundamentally limits the quality of the data we can collect. You mentioned in vivo trajectories.
Right. For AI models to be robust, they need to see successful movements, they need to see failures, near failures, recoveries.
The edge cases.
All the edge cases, and they need to see them executed in diverse anatomical settings. But ethically and legally, we are extremely limited in gathering trajectories inside a living patient, especially any data that involves a near failure or a recovery maneuver.
Of course.
And then patient privacy regulations further complicate the aggregation and sharing of what little high-quality data does exist. It just creates a small, biased, and non-generalizable data set.
So we have scarce real data, which pushes researchers toward relying on synthetic data generated through simulation.
Right.
Yet the sources explicitly state that existing physics-based simulators struggle profoundly. What specific aspects of the surgical environment do these simulators fail to capture?
They encounter what the researchers term the visual and dynamic domain shift. I mean, think about general robotics. Moving a box or assembling an electronic part, those are rigid, predictable objects. Surgery involves soft tissue, and that requires complex, high-fidelity modeling that simulators they haven't mastered it yet.
So what are the biggest technical failures? Where do they fall down?
Well, visually, the environment is incredibly difficult to render realistically. We're talking about endoscopic video, which is a key source of data. So that means a very narrow field of view, bright, highly concentrated lighting, and the presence of fluids, blood, saline, things like that.
And the reflections, I imagine.
Oh, crucially, soft tissue is often highly reflective, creating these intense specular highlights. If the synthetic video rollouts don't capture that exact visual complexity, like the way light bounces off a wet artery wall, for instance, the resulting robot policy will fail in the real world.
Because the visual input it expects just won't match reality.
It won't. And dynamically, the soft body physics must be nearly impossible to model accurately.
That feels like the real challenge.
It is the single biggest challenge. When a robot grasps or cuts or sutures tissue, that tissue deforms non-linearly. The tensile strength of various tissues, fat, muscle, fascia, it differs dramatically and is highly unpredictable. When you push a needle through tissue during suturing, the tissue creates countertension. Simulators struggle to accurately model that dynamic feedback loop. So if the simulator predicts the tissue yields easily, but the real tissue is tougher.
The robot applies the wrong amount of force.
Exactly. It applies the wrong amount of force in the real world, and it could potentially tear the tissue or even break the needle. The fidelity of soft body simulation is it's simply not high enough to bridge that gap between the synthetic and the real.
That's a powerful analogy. This isn't like driving a car on a simulation where the road surface is rigid.
No.
This is more like trying to perform a complex, delicate task on a medium that is constantly changing shape and resistance in unpredictable ways.
Precisely. If the simulator can't model that, the robot policy trained on it will fail the moment it touches real tissue.
Which brings us back to the vast, untapped resource. This huge corpus of unlabeled surgical videos. These are the video surgeons watch for training, but they contain no mechanical data.
Yeah, they exist in abundance, from public datasets like GRASP or SAR50 or credentialed channels on YouTube. These videos show expert surgeons executing procedures perfectly. They are visually high fidelity, but they lack the corresponding mechanical action labels, the kinematics that a robot needs to learn.
So we have this disconnect. We have the visual what's and maybe the language how from transcripts or commentary, but we're totally missing the mechanical do.
And that missing do, the action vector. It renders these videos useless for policy learning methods like imitation learning. This is why we keep emphasizing the reliance of modern policy models on vision language action datasets.
Right.
They don't just need to understand the general action, they need the mathematically precise 20-dimensional output that the robot generated at that precise millisecond to achieve that micro movement.
So SurgWorld, therefore, is essentially creating that missing do column for millions of frames of video. It's the ultimate data multiplier, enabling the application of these powerful VLA foundation models in a domain where previously they were just starved.
And the approach of inferring this data is so radically different from trying to simulate the complex physics, which has just proven too difficult. They are learning the relationship between vision and action from a few real examples and then applying that knowledge universally.
Okay, so to build this framework, they couldn't just throw raw, unlabeled video at a world model. They first had to create a meticulously curated foundation. That brings us to the Surgical Action Text Alignment, or SATA Dataset.
Yes.
This feels like the ultimate human investment required to launch the AI.
It was an incredible feat of human labor. SATA is the dataset that grounds the world model in the nuanced reality of surgical motion and language. It consists of 2,447 expert-annotated video clips, spanning over 300,000 frames of surgical activity. Now, while 300,000 frames might sound small compared to, a billion internet images,
For this domain, that's massive.
for surgical data where every frame has to be checked by an expert, the scale is absolutely massive.
And they didn't start completely from scratch. They aggregated and re-annotated material from existing public datasets, SAR RP50, Multipass 140, HICO, and mixed them with data from credentialed surgical YouTube channels. Why was that aggregation and re-annotation process so critical?
Standardization, that's the key. Existing datasets often use different labeling schemes, or they focus on these high-level semantic labels like suturing is occurring.
Which is useless for a robot.
Completely. SurgWorld needed to standardize all of this under one precise schema designed specifically for physical AI. They weren't interested in general semantic reasoning. They needed the granular detail necessary for a robot to execute a precise, controllable physical task. This curation step ensured the text descriptions were physically actionable.
Let's talk about the complexity of the task they focused on. Needle handling and suturing. This is arguably one of the highest dexterity requirements in robotic surgery.
For sure.
And they successfully decomposed this complex procedure into 4 core trainable primitives.
They did. They essentially broke the choreography of suturing down into its foundational movements. Mastery of these 4 movements, when recombined, allows the robot to perform the entire complex procedure.
Okay, let's run through those 4 actions, and I want to hear why each one is critical from a robot control perspective.
All right. First, we have needle grasping. That's 689 clips. This isn't just a static act of holding the needle. The annotation focused intensely on the smooth, dynamic go-to-grasp motion.
The approach.
The approach. The robot needs to learn the precise trajectory and speed required to approach the needle and secure it in the jaw of the instrument without damaging the delicate, curved structure. If that grasp is off by a millimeter, the subsequent puncture will fail.
And the second one is the most high stakes, I imagine. Needle puncture. It's the largest category, too, with 989 clips.
This is where that physics challenge, the soft body deformation, is most acute. Puncture requires immense precision. The annotations focus on controlling the needle's entry angle, its path, and its depth into the tissue, all while counteracting the tissue tension we discussed earlier.
So it's pushing and rotating at the same time.
The robot has to maintain consistent forward force while executing a complex rotational movement to follow the needle's curvature. This single action is a microcosm of the entire soft robotics problem.
Then we have suture pulling, 475 clips. That sounds simple, just pull the thread. But why is it a distinct primitive?
Because of friction and potential snagging, suture pulling requires smooth, measured force application to draw the thread through the tissue without excessive tension.
Which could tear it.
Exactly. It could tear the suture track or pull the knot loose. So the AI needs to learn the kinematics that correlate to maintaining constant, non-damaging tension.
And finally, knotting, with 294 clips.
The complex looping and tightening motion required to secure the tissue. Knotting demands incredibly precise coordination between both robotic arms, one holding tension, the other looping the suture, and then tightening the entire structure to the exact tension needed to secure the tissue without crushing it.
So by breaking the procedure down into these 4 digestible, trainable primitives, they gave the AI the building blocks for composition.
That's it.
The decomposition is clever, but the truly innovative leap, in my opinion, lies in the specificity of the text annotations accompanying those clips. It wasn't robot holds needle, it was like microscopic detail.
Correct. The researchers knew that strong text-video alignment was the key to generating future novel actions. So the text descriptions capture 3 layers of information that a surgical robot absolutely requires.
The first being precise tool-tissue interactions.
Meaning, did the tool cut? Did it grasp? Did it retract? This level of detail tells the robot the purpose of the action. Hassan, they capture the spatial relationships between instruments.
Okay.
For bilateral tasks like suturing, the robot needs to know where the left instrument is relative to the right, and crucially, relative to the tissue in the endoscope camera.
And the third layer, this is what grounds the action, the real medical context, anatomical context.
This is where the human expertise really comes in. Instead of a generalized annotation like, the tool grasps the tissue, a SATA annotation might read, the left needle driver punctures the right side of the patient's dorsal venous complex, starting 2 millimeters from the previous stitch.
That's incredible. It's linking the visual event to a specific instrument, a precise physical outcome, and a clinically relevant anatomical structure.
It's not just labeling the action, it's providing the reason for the action in clinical terms. This allows the model to learn not just what motion occurred, but why it occurred relative to the context, which is essential for safe, autonomous generalization.
It's essentially turning every video clip into a paragraph from an expert surgical textbook, one that's fully searchable and actionable by the AI.
And that depth is the expensive, critical human investment that makes the rest of the framework possible.
Okay, so with the SATA dataset in hand, they move to the engine itself, the SurgWorld architecture. This is where we see the fusion of a massive general foundation model and highly specialized surgical knowledge.
Right. SurgWorld is built on a state-of-the-art foundation model called Cosmos Predict 2.5, which uses a diffusion-based latent video prediction. The critical point is that this base model is already pre-trained on diverse, general, robotic, and embodied datasets.
So it already understands physics.
It understands basic physics, how objects move and interact, and how videos change over time.
So they didn't have to teach the model how to be a video generator. They just had to teach it how to be a surgical video generator. That must save a tremendous amount of time and compute.
Yeah.
How did they achieve that specialization, adapting a general model to this highly specialized surgical domain?
They used the technique called domain adaptation, and specifically they employed low-rank adaptation, or LoRa. This is a computational shortcut, basically.
Okay.
Instead of retraining the billions of parameters in the massive Cosmos Predict 2.5 foundation model, which would be prohibitively expensive, they insert these small trainable matrices, the LoRa modules, into the key transformer layers.
So LoRa acts like a set of specialized glasses for the model.
That's a great way to put it. It allows the model to specialize its understanding to the unique challenges of surgery, the specular reflections, the endoscopic occlusion, the constrained tool motion, all by updating only a tiny fraction of the total parameters. It's highly parameter-efficient fine-tuning.
So it drastically reduces the computational expense of customizing the model to the OR environment, while keeping the foundational video generation capabilities intact.
Exactly. And that adaptation is what transforms the general video predictor into a surgical world Model 1 capable of generating photorealistic, temporally coherent surgical rollouts based on precise text prompts.
But as you said, generating the video is only half the battle. The video itself is useless for robot training without the control commands.
Right.
This brings us to the inverse dynamics bridge, the IDM, which is the absolute pinnacle of this framework.
It really is.
This is the pivotal technical achievement that generates usable action data, pseudo-kinematics. Let's pause and really explore what an inverse dynamics model does in this context.
Okay, so an IDM fundamentally reverses the prediction problem. A standard dynamics model predicts the next visual state given the current state and a set of actions.
What will happen next?
Right. The IDM does the opposite. It looks at a visual transition, say, a needle moving from position A in frame 1 to position B in frame 16, and it predicts the specific robot actions, kinematics, that must have occurred between those two frames to cause that exact visual change.
It's retroactively writing the instruction manual for the video we just watched.
Perfect. It is inferring mechanical intent from visual change. Now, to make this inference reliable in the surgical context, the IDM is first heavily pre-trained on real out-of-domain episodes. They used about 60,000 action frame pairs depicting general robot movements.
Not even surgery.
No, this might be generic grasping or manipulation, not specific suturing.
Why is that pre-training necessary? Why not just use the surgical data?
To give the IDM a foundational, transferable understanding of basic robot kinematics. It teaches the model the general relationship between how a robot arm moves in 3D space and how that movement translates to pixels changing in the camera feed. Once it understands general movement, it only needs a small amount of surgical data to specialize in the fine motor control required for needle handling.
This is also where the conceptual tension lies, which the critique highlighted. We are now trusting inferred data pseudo-kinematics that was never physically measured by a sensor. What is the inherent risk of training a safety-critical system like a surgical robot on non-ground truth action labels?
The risk is noise and inaccuracy, and that could potentially lead to unsafe movements. If the IDM slightly misinterprets a rotational action needed to pull a suture, the subsequent policy trained on that mistake might tear the tissue. The success of SurgWorld absolutely hinges on the IDM's ability to generate pseudo-kinematics that are accurate enough to be beneficial, even if they aren't perfect ground truth. The researchers had to prove that the sheer volume of high-quality synthetic data offsets the residual noise introduced by the inference process.
Okay, let's synthesize the entire four-step workflow now, because this is the process that creates the scalable, paired video action data.
Okay. Step 1. SurgWorld is initially trained, fine-tuned on the high-quality SATA dataset. This grounds it in the surgical domain, teaches it the visuals, the language, and the correlation between the two. Step 2. SurgWorld and the IDM are then fine-tuned on a very small, robot-specific, real dataset. This is the calibration step. It adapts the world model and the inference engine to the specific dynamics, latency, and visual signature of the exact robot hardware being used for the downstream tasks.
So it's tailored to the final physical system.
Precisely. Step 3. SurgWorld generates diverse, generalizable, synthetic video rollouts based on text prompts. This is the data multiplier phase. You can generate hundreds of hours of video from prompts like, execute a 2-time needle handover.
And then the IDM labels it.
Then, the IDM infers the pseudo-kinematics for those newly created synthetic videos, generating the crucial scaled video action pairs. And finally, step 4. The final VLA policy, in their case, the GR00T N1.5 model, is trained on both the scarce real data and the abundant synthetic data. The small amount of expensive real data validates the quality, and the huge amount of synthetic data provides the scale and diversity needed for generalization.
That's true leverage. You use the few real samples to teach the IDM what a real action looks like, and then you apply that action-visual relationship to an infinite supply of synthesized videos. You've dramatically shifted the data bottleneck from collection to computation. Now, before we look at the validation, let's get into the technical specificities of what the robot is actually being asked to control. When we talk about kinematics, we are dealing with continuous numerical vectors. The source material details a highly complex 20-dimensional action space. For the listener interested in the mechanics, what does this 20D vector encode at every millisecond of movement?
It's a dense, continuous vector that describes the state change of both instruments operating simultaneously. The 20 dimensions are split equally, 10 dimensions for the left instrument and 10 for the right.
Okay, so think of it like trying to control two independent, highly articulated, perfectly coordinated hands with 10 continuous control knobs for each. What are those 10 controls for a single instrument?
They are broken down into 3 physical components: position, rotation, and gripping. First, we have p-dialers, the translational offset. This is a 3D vector $6 YZZ measured in meters. This tells the robot how far to move the tip of the instrument in Cartesian space relative to the endoscope camera frame. So basic positional change. Second is $3, the rotation representation. Now this is the most complex part, and it uses a 6D vector, and they specifically chose a 6D representation instead of the more common 3D Euler angles or quaternions.
Why the jump to 6D rotation? Why not use the standard 3D representation?
Because 3D rotation representations in neural networks are prone to discontinuities. You get what's called gimbal lock, or these sharp jumps when the robot moves close to certain angular limits. This creates massive errors during training and execution.
Which would be catastrophic in surgery.
Absolutely. Using a 6D representation ensures smooth, continuous interpolation in space, which is vital for the precise, fluid orientation changes needed for complex surgical tasks like threading a curved needle. This guarantees that small changes in the action vector result in small, predictable, physical changes in tool orientation. So that's 3 dimensions for translation and 6 for rotation. The final dimension is $D, the gripper jaw opening, measured in radians. This tells the robot exactly how wide the forceps should open or close.
So 3 position plus 6 rotation plus 1 jaw equals 10 dimensions per arm. 2 arms equals 20 continuous dimensions. That is an incredibly high fidelity, fine level of control precision the inverse dynamics model is attempting to infer from a video transition.
And the subsequent success of the policy depends entirely on how accurately the IDM can predict those 20 numbers, millisecond by millisecond, across a long synthetic video rollout. This sets a very, very high bar for the fidelity of the world model itself.
We have the sophisticated engine, the SurgWorld model, and the crucial bridge, the IDM. Now, for the big question, did it actually work? This is where it gets interesting, because they had to prove 2 things. First, that the videos were realistic, and second, that the new behaviors the model generated were plausible.
Right. The first step was validating the output quality. If the synthetic videos look like a low-fidelity simulation or a cartoon, the inferred kinematics, the pseudo-kinematics, will be garbage.
They used a key metric here, Frachet video distance, FVD. For our listeners who may not be steeped in computer vision metrics, what is FVD?
FED is a standard metric used to assess the quality of generative video models. It measures the perceptual distance between the generated videos and a set of real ground truth videos. Essentially, it assesses both perceptual realism, how good does it look, and semantic coherence. Does the motion in the video make sense temporally and logically?
So lower is better.
A lower FVD score indicates videos that are perceptually closer to reality and more temporally consistent.
They compared SurgWorld against 2 variants based on the same Cosmos Predict 2.5 foundation, a zero-shot model with no surgical adaptation and an action category model fine-tuned only on course labels. What were the numbers?
The results were definitive. SurgWorld achieved the lowest FED score by a huge margin, 106.5. Contrast that with the zero-shot baseline at 175.4 and the action category model at 143.0. A score of 106.5 is excellent for a complex diffusion-based video generation task.
So it confirms that the detailed SATA pre-training is essential for achieving that superior realism.
Superior perceptual realism and ensuring the movements within the synthetic video follow the natural physics and dynamics of the surgical domain. Yes.
Beyond the raw numbers, the qualitative difference they highlight proves the value of the SATA dataset's text grounding.
It really does. They give an example where if the initial frame showed no surgical tools, the zero-shot model lacking domain knowledge would often hallucinate the wrong instrument or start an action incorrectly. The action category model, which had only course labels, might start a grasping action when the text prompt specifically requested a puncture. But SurgWorld, grounded by the fine-grained text of SATA, correctly initiates the intended motion, say, the needle grasp, with correct tool consistency and anatomical placement. The text is truly dictating the visual output.
I have to admit, the results on generalization were the most surprising part of the paper. This section on new behavior generalization is the true aha moment. It suggests the model is learning the grammar of surgical motion, not just memorizing training clips.
Absolutely. This is the holy grail of world models, the ability to extrapolate and combine learned primitives into novel sequences. During the initial curation of the SATA dataset, all complex movements, like multi-time handovers, were segmented and labeled as individual single handovers.
Meaning the model was never explicitly trained on a sequence of, say, arm A handing the needle to arm B and then arm B handing it immediately back to arm A.
Correct. It never saw that. Yet, when they conditioned SurgWorld using a text prompt describing a 2-time needle handover sequence left to right, then right back to left, the model accurately generated a long, temporally consistent, and anatomically plausible video rollout of that novel composition. They even successfully generated a 3-time handover sequence.
That is profound. It demonstrates that the policy learned the atomic actions, the grasp, the release, the transfer trajectory, and successfully recombined them based solely on a high-level, novel textual instruction. Why is this capability so crucial for scalable surgical AI?
Because it breaks the demonstration bottleneck entirely. If the model understands the compositional structure of the task, you don't need a human expert to demonstrate every possible permutation and combination of a procedure. You only need to describe it clearly in language, and the AI can generate the necessary training video, which is then labeled with pseudo-kinematics by the IDM.
It accelerates skill acquisition exponentially.
It does.
But no matter how good the FVD metric is, or how well the model generalizes, the ultimate validation must come from the human experts sitting in the operating room. Did they bring in surgeons to assess the clinical plausibility?
They did, and this was crucial. They conducted a human expert evaluation. They involved a team of 3 surgical experts, a surgeon supervising 2 residents who independently assessed 50 generated video samples. And the key here is the assessment criteria, which moved far beyond simply, does the video look real?
So what were the criteria that defined clinical plausibility?
The experts used a 1 to 3 quality rubric, where 3 was the highest quality. The first criterion was text-video alignment, ensuring the generated scene faithfully matched the prompt and the surgical viewpoint. The second was tool consistency, making sure the instruments behaved physically consistently, avoiding unrealistic deformation, floating, or discontinuity, a major pitfall of generative models.
And the third?
And the third, and perhaps most critical, was anatomical structure, measuring the plausibility of the tissue behavior. Did the tissue deform realistically? Did it react to traction as expected? Did the needle enter the correct plane?
When a surgeon says a synthetic video is clinically plausible, that's a massive regulatory and psychological hurdle cleared. How did SurgWorld fare?
It achieved superior average scores across all 3 dimensions. For text-video alignment, it scored 2.82, for tool consistency, 2.81, and for anatomical structure, 2.73.
Wow.
The comparative models, especially the zero-shot variant, struggle significantly, particularly with anatomical structure dropping below a 2.0. This just validates that the fine-grained SATA annotation and specialized LoRa fine-tuning are absolutely essential for generating videos that are not only realistic, but clinically faithful and safe enough to potentially be used for policy training.
That strong clinical affirmation demonstrates that the framework is generating high-quality instructional content. Finally, they prove the framework's efficiency with the few-shot adaptation success. This is crucial for real-world deployment.
Yes, the few-shot experiment was designed to prove that the expensive investment in SATA pre-training acts as a powerful prior, drastically reducing the amount of real-world data needed for a new task. They tested 3 configurations, all using only 5 real-world trajectories from the needle pickup and handover task.
5 trajectories.
Yeah.
That is the definition of data scarcity. In general robotics, that's nothing.
It's almost negligible. Yet the SurgWorld model, which was SATA pre-trained and then fine-tuned on those 5 real trajectories, achieved a 73.2% success rate on generated trajectories.
That's huge.
It substantially outperformed the model fine-tuned directly from the base checkpoint, which only managed a 51.8% success rate, and the zero-shot model, which failed completely, 0%.
This means the knowledge contained within the 300,000 SATA frames effectively gave the model a massive head start, allowing it to adapt to a new robot embodiment with high proficiency, even with almost no new real data. It fundamentally changes the required investment profile for surgical robotics deployment.
It proves that the framework provides a robust, generalized understanding of surgical kinematics, which is the most valuable asset in a data-scarce environment.
Okay, so far we know SurgWorld creates excellent synthetic videos, and the IDM labels them with pseudo-kinematics. The final, most important test is this. Does training a robot policy on this synthetic data actually lead to better performance on a real surgical robot than training on real data alone?
This is the real-world validation. The rubber meets the road, or in this case, the needle meets the pad. They tested the trained policies on a commercial endoscopic surgical robot performing the dexterity-intensive needle pickup and handover task on a physical rubber pad. They used GR00T N1.5 as the policy engine, which is a state-of-the-art VLA model.
And the success metric here shifts entirely from video quality from FVD to control accuracy. They focused on the mean square error, MSE, comparison of the 20-dimensional action prediction between the ground truth and the trajectories predicted by the trained policies.
Right. Lower MSE means the robot is executing movements that are closer to the expert demonstration.
The experiments systematically varied the amount of real training data, 5, 10, or 20 episodes, and compared policies trained only on that real data, the real-only group, against policies augmented with synthetic data.
Yeah, 56 or 560 synthetic rollouts.
So what was the overwhelming core finding when comparing the real-only policies versus the augmented policies?
The core finding was highly consistent. Policy models trained with synthetic data consistently showed lower average MSE, meaning better action prediction accuracy, than models trained only on the scarce real data across all tested amounts of real data.
Wait, let's just take a moment to absorb that. The synthetic data, where the kinematics were only inferred.
The pseudo-kinematics.
Right, the pseudo-kinematics, which contained residual noise, was effective enough to teach the robot to move more accurately than if it had only seen the real perfectly measured data.
Yes.
That's a powerful validation of the IDM's quality and the value of scale.
It is the vindication of the entire synthesized approach. The small sample of perfect real data lacks the diversity needed for generalization. The large volume of synthetic data, even with minor noise, provides the VLA policy with a much broader and smoother distribution of successful trajectories. It essentially acts as an incredible regularizer.
And the impact of scale within this synthetic approach was clearly seen in the results.
Absolutely. The policies trained with the $10 times synthetic data augmentations, so the 560 rollouts, showed the lowest overall MSE. And this improvement wasn't localized to just one part of the control vector. It held true across all physical components of the 20-dimensional action vector: translational, rotational, and jaw actions for both the left and right arms.
Let's break down the implications of reducing MSE in those specific components. Why is reducing rotational MSE particularly important for safety and effectiveness?
Rotational accuracy is paramount in surgery. Suturing involves grasping a curved needle and rotating it precisely through tissue. If the rotational MSE is high, the robot's predicted path for the needle will be jerky or misaligned,
Which could lead to dropping the needle.
or requiring a complex retrieval maneuver, or worse, tearing the tissue due to incorrect angular forces. Lowering the MSE on that complex 6D rotational vector means the robot can predict and execute the nuanced orientation changes needed for precise needle handling with higher fidelity, which translates directly to reduced risk of error in the operating field.
And what about translational, the Cartesian error reduction?
That's fundamental for positioning. It means the robot is placing the tool tip in 3D space much closer to the expert's demonstrated location. If the translational error is low, the robot is less likely to miss the target insertion point or collide with other structures.
And there was a visual confirmation of this in the paper.
It was referenced in the paper, showing the left arm's Cartesian trajectory in 3D space, and it vividly illustrated this. The trajectory predicted by the real plus sin 10x model just hugged the ground truth expert path far, far closer than the real only model.
It's proof that scale, even synthesized scale, is winning. The synthetic data effectively smooths out the rough edges of the limited real-world data, preventing the policy from overfitting to a small number of possibly idiosyncratic expert demonstrations.
It helps the policy avoid what's called covariate shift, which is the common failure mode when imitation learning only has scarce data. The policy sees too few examples, learns specific quirks of those examples, and then fails spectacularly when placed in a slightly different environment. The synthetic data provides the necessary diversity to prevent that brittleness.
And they confirmed that this performance boost wasn't isolated to just one specific VLA policy model or a single camera view.
And that's a critical point for general applicability. They showed the performance gains held true even when training multi-view policies, proving that even though SurgWorld generates single-view synthetic videos, the kinematics inferred are robust enough to improve policies utilizing multiple camera inputs. Furthermore, they successfully replicated the performance boost when they substituted the GR00T N1.5 policy model with another major foundational VLA architecture, Pebble 5 cents. This confirms that the benefits stem from the synthetic data generation approach itself, the combination of SAT and the IDM, rather than just being an optimization artifact specific to one robot policy model.
This suggests that SurgWorld offers a truly modular and scalable methodology that can be generalized across the heterogeneous landscape of surgical robotics development. So, to summarize the breakthrough here, SurgWorld marks a critical milestone. It's the first surgical world model to successfully use synthesized video action data to train high-performing surgical robot policies. It addresses the core data scarcity issue head-on, opening a viable path toward scalable and robust autonomous skill acquisition.
It transforms the developmental cycle for surgical AI, pivoting from impossibly expensive data collection to smart data generation. However, the researchers were very transparent about the current boundaries of the framework, and understanding these limitations is crucial for future development.
Okay, let's review those self-assessments. What are the key areas where the framework still needs refinement?
First, there is the limitation of embodiment specificity. While the world model is highly generalizable, Adapting the final system to new, unseen robot hardware, say, moving from one manufacturer's system to another, still requires a minimal fine-tuning data set specific to that new embodiment.
Right.
The IDM needs that small, real-world sample to learn the specific physical constraints and visual characteristics of the new robotic arm and camera system.
So it's not a magical zero-shot transfer to every robot in existence yet.
Here.
Minimal calibration data is still required.
Precisely. The second limitation is the inherent noise introduced by the inference process. As we discussed, the kinematics inferred by the IDM are pseudo-kinematics. They are not ground truth measurements.
Right.
And while the policy benefits from the volume, the process still introduces residual noise into the action labels compared to what an actual sensor would record.
That means continuous refinement of the IDM is necessary to tighten the precision of those predictions.
Absolutely. Future work must focus on optimizing the IDM to make its pseudo-kinematics cleaner, reducing that residual noise without sacrificing the scalability gains. And finally, there's the limitation related to data coverage. The SATA dataset, while powerful, does not yet encompass all available public surgical datasets or the full range of complex procedures.
So to make SurgWorld truly universal, the future involves continuously extending SATA to cover more complex multi-step procedures beyond just suturing and a broader diversity of surgical environments.
The path forward is iterative,
Yeah.
continuously expanding the human knowledge base in SATA and simultaneously refining the IDM to improve the precision and clinical fidelity of the pseudo-kinematics. The aspiration is a fully autonomous, safe, and highly generalizable surgical AI that can learn complex new skills with minimal human demonstration.
This entire framework rests on the power of combining expert human knowledge, captured in those highly detailed text annotations, with the generative power of world models.
This raises an important question. Is text-guided synthesis the true shortcut to zero-shot surgical mastery? I mean, the level of generalization demonstrated, like generating complex multi-time handovers based solely on text, it hints at a future where the AI understands the abstract concepts of surgery, guided purely by language.
The model learned how to execute actions it had never explicitly seen demonstrated. So, if robot policies can accurately generalize complex movements based only on verbal instruction, could the next logical step be instantaneous? Verbal customization in the OR.
Imagine the scenario. A surgeon is faced with a novel anatomical challenge or a complex unforeseen complication. Instead of manually struggling with the controllers, the surgeon provides a novel, highly complex command in plain language, detailing a motion sequence never before encountered in any data set.
A command like, grasp the left vessel wall at a 45-degree angle, utilize the reverse throw technique, and tie a double locking knot with half the standard tension.
Precisely. And the robot, leveraging a perfected SurgWorld model, instantly generates the pseudo-kinematics for that precise motion based on the language input and executes it immediately and safely. This capability would entirely redefine the training and the role of human surgeons.
They move from being meticulous joystick operators to providing real-time, high-level, language-based task customization.
It transforms the surgeon into a conductor, leveraging the AI's compositionality.
It's a truly fascinating implication for the future of medicine, where expert language becomes the primary interface for autonomous skill acquisition.
It suggests the policy is achieving mastery through concept composition, guided by the highest level instructional modality available, expert language. And that is where the real deep dive into the future of surgery begins.